All right, guys. So the next chapter 4 topic that we're going to be talking about is the electron waveforms and atomic orbitals. So again, let's go back to our slide. So this is really the theory, we're really getting into the chemistry right now. It's the theory of the atom, right? So we don't know exactly what the atom looks like. It's way too small, right? We can't even use a microscope like something in biology class and we look at a cell. We cannot look at the atom directly. Um, but we have theories that have been corroborated for centuries, and it's pretty solid, right? And so that's what our whole society is built on, is based upon, are these theories. And a very one important theory is the atomic theory, right? What is the atom and what is inside it, and how does, these things affect all the things that we see around us, right? How are we able to use this theory to benefit us, right? In terms of the materials we're able to build, the medicines we're able to create, the technology that we've built around us in order to make our lives easier and to survive, right? This hinges all of these things, everything around you hinges on this atomic theory. Uh, Um, Now we are in a introductory chemistry class, so we are not going to go too much in detail about the theory, which is really beyond the scope of this class. You would need to be a senior in your senior year, right? You guys are in your freshman year, so we're not gonna go that much into depth, but I'm just gonna give you the gist and the bits and the pieces so that you have enough in order to understand what the atom is. Okay? Now, the problem with, and really in a nutshell, why chemistry is so hard. Well, for one, right, we can't see the atom, we can't see the electrons directly. But it's much worse than that. It's that because the electrons and the atoms are so tiny, their physics is totally different than our world's physics. Our world's physics deals with, large particles. Electrons are extremely tiny and they play by a different rule. So the problem with the electron is, you know, just at the basis of the problem is that we cannot know where the electron is at at any given time because it's moving so fast. The electron travels only 100 times slower than the speed of light. And because it's traveling that fast and it's so light, we actually cannot pinpoint with certainty, 100% certainty, where the electron is. Okay. And so that's where probabilities come in, right? So what we can say, right, probabilities wise, is that we can, say the electron is probably going to be here to this degree of certainty. And that's good enough for us, right? Well, we've done a good enough approximation in order to make all these advancements to solve a lot of problems. So that's what it is, okay? And since it's so complex, what we're going to do is we're going to use analogies in order to communicate what the nature of the electron is. Okay? So to just illustrate how complex this topic is, not even the experts in the field know exactly what's going on because we just cannot comprehend that level of complexity. Um, so the analogy that we're going to make is to a guitar string. So if you guys ever, you don't have to play the guitar, but if you ever seen a string being struck, you know that it's fixed on both ends. So when you pluck the guitar string, it vibrates. And it can vibrate in several configurations, right? As you can see here, there's, 7 possible motions that can go through, right? As it's vibrating up and all the way down. Um, and if you superimpose these on top of each other, what you see are what we call a standing wave, because you have these nodes here where things don't move, and then you have here amplitudes of waves that are moving. So this is considered one waveform, right, in which a guitar can um, express its energy, right, when you pluck it. Okay. And here are other allowed vibrations for that guitar string, right? This is the simplest, right? Where that's if you just pluck it, very lightly, it could just go up and then it goes down, right? Swings up and down. Or it can have this waveform here, right? But it can have infinite, actually, waveforms. So many other more complex ones, okay? But they're all representation of a standing waveform. We're going to use that analogy and we're going to put it to the electron, right? The electron has wave characteristics as well. The electrons is both a particle and a wave, right? And we can observe both of them at the same time. So for a lot of times, we just either observe the electron as a particle or a wave. And the wave character of the electron is very complex, but we can make an analogy to the guitar. So the different waves form of the electron, it's basically how it varies its charge density. So the electron is negatively charged, right? So one electron is one minus. Now, each waveform would be the various different ways that the electron will distribute that negative charge, okay? And through what region of space it's going to do so. And so those are the different possible ways that it can disperse its negative charge. It's basically the electron waveform. And we'll see later that these are called orbitals, okay? So we'll get more into that in a second. But first, I want to show you guys the Bohr model of the atom, because we are talking about the atom, which we cannot directly observe. And so we have to use our imagination. And Bohr model of the atom, even though it's really simplistic, and it's sometimes called the solar system model of the atom, it's highly inaccurate, okay? But it does have its uses. So I'll tell you what those are, okay? The Bohr model atom is not realistic at all, okay? Electrons do not just move in fixed circular orbits like this, but it is kind of useful to kind of have that mental picture. What is true, though, is that the atom is somewhat spherical, right? And so you can imagine that it's a sphere, and in the middle is the nucleus, okay? And these n is equal to 1, 2, 3, 4, 5 are basically concentric spheres radiating from the nucleus. And you can think of those as energy states where the electrons can be, okay? So let's say that we are thinking about the Bohr model of the hydrogen atom. The hydrogen atom has one electron, right? So the one electron of hydrogen can be really close to the nucleus, and we would call that the most stable state, n is equal to 1, okay? But if it can absorb enough energy, it can jump to 2, 3, 4, or 5, okay? And how you define how large an atom is how far the electron can stray away from the nucleus, okay? And so the gist of it, right, is that electrons can move to different energy states. And the energy states radiate out from the nucleus, much like a ladder, okay? And these are called the principal quantum number. Don't worry about what quantum numbers are. Just think of each, excuse me, each number as how far you are from the nucleus. So if your n is equal to 1, that quantum number means you're closest to the nucleus. And if your n is equal to 6, you're furthest, right? Just going back and looking at this, right? Or if you're 5, you're further. 4 is you're closer to the nucleus, okay? So these shells, these concentric shells, are basically describing where the electron can be. And it also describes the size of the shells, right? So if you're in n is equal to 1, you're in a smaller region of space. Then if your n is equal to 2, you're in a larger region of space, right? So the Bohr model tries to explain where the electron is. So let's say that the electron is n is equal to 1 right now. If energy is absorbed by this electron, then it can get excited. So that is called excitation, and the electron can move to a higher energy state. Let's say that this is n is equal to 3, okay? But eventually, as it's moving, the electron will lose energy, and it will fall back down to its home state. We call this the relaxation, Okay, so it can relax back to energy state 2, and then eventually it will relax back to, we call that the home state, n is equal to 1. Okay. So this shows basically the energy transfer that can happen with the electron. So the electron can absorb energy. It would be an endergonic process, right? And it gets excited to a higher energy state. And then when it relaxes, when it goes to a lower energy state, that's called relaxation, and it releases that same amount of light that it absorbed. Okay. So some terms you should know, right? So if the electron is n is equal to 1, we call that the ground state. And then when it gets excited to 2, 3, 4, 5, we call those the excited states. Okay. And it can hop one step or it can hop several steps, right? It just depends on how much energy that it gets. So what happens is, let's say that hops from, 2 to 5. Okay, if it hops from 2 to 5, that means it absorbed enough energy to get to the energy level 5. Now, from energy state 5, it will eventually have to lose energy and fall back down to 2, in which it will release a light. And that light, since it corresponds to a higher energy gap, would correspond to a higher energy light. And so that light that we would see would be purple. Okay. And then the light that you see, let's say from energy level 4 to energy level 2, that is a smaller energy gap, right? Than from 5 to 2. And so that would manifest as, say, blue-green light, okay? And if the electron goes from 3 to 2, that's a very short energy gap, right? It's low energy. So lower energy light is red, okay? So Bohr model of the atom explains the atomic emission spectrum of hydrogen. Now, the atomic emission spectrum is when you guys see neon lights, right? And you see these lamps that are like really brightly colored. That is basically what's happening here. It's the electrons are getting excited and they're falling back down to a lower energy state and they're giving off that whatever color light corresponding to the energy gap. Okay. And so that's what it is. That's how the Bohr model can explain these colors that we see from different um, uh, 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 lamps of elements. Okay, so the Bohr model of the atom, like I said, not it can only explain it for hydrogen for one, but it's not accurate at all, right? It's implies that the atom is like the solar system where the nucleus is like the sun. It's not at all like that. So definitely that's the failure of the Bohr model, but it does give us a nice just initial image, of the gist of what the atom kind of looks like, right? Really the be all end all theory that we've been using is called the quantum mechanical model of the atom. And this one is very complex. It was developed by Erwin Schrödinger, and he basically applied mathematics of probability and the ideas of quantizing energy to the physics equations that describe waves. And when he solved for the solutions, what he found was that these wave functions, which describe the probability of finding the electron in certain regions of 3D space within the atom. And that's what we've been using to do all our calculations, to do all of our chemistry and physics ever since. Again, it's beyond the scope of this class. We're not going to go into depth with it, but I'm going to show you the results of the quantum mechanical model and the solutions and how to interpret them. So what came out of this model is orbitals. Okay, so orbitals again was right how the electron wave functions could express itself in different ways. But the easier way to think about it is just think of it as a 3D region of space where you have a very high probability of finding the electron within that space, right, within the atom. The certainty is generally set to 90 to 95% because we are unable to figure out, 100% where the electron is at any given time because it's moving so fast. Okay. So here are the answers, right? Here are the atomic orbitals. Um, uh, uh, they are designated with letters, and the letters correspond to the shape, where the numbers in front correspond to the principal quantum number, the shell, or the size, right? In Bohr's model, it's the same idea, right? Remember in Bohr's model, the higher the number, the larger the concentric shells and the larger the size, okay? So the number in front tells you how big that region of space is. And then the subshell, which is the letter, tells you the shape, which means like, where can I find, right? What is the shape of this space where I could probably find the electron? So we have 4 different letters so far. There's actually more, but we only have enough elements that we need 4. You guys don't need to know F, but I do want you guys to know S orbitals, P orbitals, and D orbitals. And so we're gonna go through and see what those look like. Okay. So again, I remember when I was a student, and every time I heard the word orbital in lecture, like my eyes would glaze over and then I would just tune out. And that's definitely not something that I want to do with you guys. Okay. So I don't want you guys to be like that. And here's why. Orbitals is actually a very simple definition. Okay. So remember, it's just the 3D region of space where you can probably find the electron. Okay, to about 90% certainty within the atom. Okay, that's all it is. So if you're looking at an s orbital, then here's the region of space in which you can find the electron. Okay, and what shape is that? It's a sphere. Okay, and each one of these dots, by the way, represents just one single electron. So the Schrodinger's equation was solved for just the hydrogen atom. But the hydrogen atom only has 1 electron. But why do you see so many dots then? It's basically the electron snapshots of the electrons at different time, right? Because the electrons never stay still. It's always in motion. So imagine having a camera and just consistently doing this, and each picture shows the electrons in different spots. And when you overlay those pictures, you basically get an electron density map to see where the electron most likely is, right? So what you can see right away from this picture is that in an s orbital, most of the time that the electron spends is around the nucleus being smack in the middle, right, of the atom. So as you go further away from the nucleus, you're less likely to find the electron, which makes sense, right? The nucleus is positively charged, the electron is negatively charged, so they want to be closer to each other. So you're going to find that the electron likes to spend its time closer to the nucleus, and the probability of finding an electron drops as you go further away from the nucleus. Okay, so that's all s orbital is. Here's another representation of it. Again, showing the electron's charge, right, or charge density with respect to the distance from the nucleus, right? And so in an s orbital, concentration of the electron's charge, right, the higher charge density is closest to the nucleus, and it, as you go away from the nucleus, it dies down, right? And of course, as I mentioned earlier, how big an atom is dependent on how far that electron can stray away from the nucleus, right? So overall, in real life, of course, it's not a perfect sphere because the electron is constantly moving, but on average, right? On average, the electron is going to move in all directions. And so it's going to approximate a sphere. And that's why we think of an atom as a sphere. Right? Okay, here's another representation of the 1s. Okay. Um, um, Another picture of a multiple exposure of that 1 electron in the hydrogen atom, right? Just everywhere. Okay, so that's what an orbital is, right? It's like if you could take snapshots of where the electron is in the hydrogen atom, just basically mapping out, right, where the electron spends, a lot of its time, right? So these pictures, are about 90 to 95%, certainty. Of course, we can't know it to 100%, but this is that probability, right? Let's talk about 2s orbital. right? So this is a 1s orbital. Remember what the 1 means. That's the size, principal quantum number. So 1 is closest to the nucleus, meaning this sphere is smaller than a 2s orbital, right? So s is still spherical. That's why it's called s. But now it's just a larger. It's further away from the nucleus. So a 2s orbital is now a larger region of space in which you can find the electron, right? So how would that, how would you picture in your mind the difference between 1s and 2s? Well, 2s is just bigger, right? Here's the nucleus in both of them, right? The 1s, the boundaries are closer to the nucleus, where n is equal to 2 is further away from the nucleus, right? Now, if you cut the 1s and the 2s, cut a cross section, you'll see that in the 2s, you have a node. In the 1s, you don't, but from the 2s and onward, you have a node, which means in this region of space, you would not be able to find an electron. And that's what a node means. The probability of finding an electron drops down to 0. Okay. Okay, so what are the other, waveforms that are allowed for the electron? We just looked at the S. There's also the p orbitals and the d. Okay, I want you guys to know all of these. So there are one type of s orbital. Notice how many p orbitals there are. 3. And the way I remember this is p like peanuts. So remember, the letter tells you the shape, right? S for sphere, P for peanut. Doesn't that look like a peanut? Okay. And there are 3 types of peanuts. So there are 3 p orbitals total. They're different in their orientation. Okay, so notice, right, they're orientated differently around the XYZ axis. So a PX lies on the X-axis, a PY lies on the Y-axis, and a PZ lies on the Z-axis. Okay, so there will always be 3 p orbitals. There will always be only 1 s orbital. And there are always 5 d orbitals. Do you see the pattern? 1, 3, 5, odd numbers only, right? 1 s orbital, 3 p orbitals, and 5 d orbitals. Okay. Now D, how do you remember that D is shaped like this? I remember as double peanut. Doesn't that look like a double peanut? Here's one peanut, here's the other peanut, right? Or 4-leaf clover. Okay. So 5 of the d orbitals, 4 of them, 4 out of the 5, have this shape, which is a 4-leaf clover. And then there's the odd duckling of orbital. It's the dz squared. It looks like a p orbital, but it has this donut, like this belt around it. Okay. And remember what these are. These are regions of space where you can probably find the electron in the atom, right? So that counts as well. So you could also find the electron in this belt region, right? I know it's weird looking, right? But these are actually real mathematical solutions. These are real mathematical functions that was found from the Schrodinger's equation, right? And why are these important? Because as you can see later on in the semester, this allows us to figure out how to describe the electron inside the atom, which is very crucial in figuring in predicting reactions, in predicting behavior, physical and chemical behavior. And so therefore, with this information, we can design things, right? We can design materials, we can make more complex things because we understand, at the very basic level, what is going on, where the electrons are, right? We call that electron configuration, and that is so important. Electron configuration dictates everything in chemistry, right? So as far as what you guys should know, I know there's quite a bit here, but I'm going to show you exactly on the board what I expect you guys to know. You should know, right, the orbitals that we went over just now. There's 1 s orbital. And to draw it, just draw a circle and label it S, okay? There are 3 p orbitals. Okay, remember P stands for peanuts. So to just draw a peanut, right? We'll first draw the axis. Okay, so you can draw X like that, Y, and Z. Okay, And the three p orbitals are the px, py, and pz. These are subscripts, okay? You should know their names, and then you should be able to draw them. This will be on a quiz, all right? This will be tested. So practice, right? Get out a piece of paper right now. Practice drawing it with me. We're gonna draw the px first. Make your peanuts lie along the x-axis. Okay. And then we're gonna draw the py. So I make my peanut lay on the y-axis. Okay, you see how that looks different, right? Okay. And then for the pz, draw your z-axis. Right, label your axis. And say pz. Okay, so now you know how to draw 4. Okay, these are easier. Okay, I don't expect you guys to have a lot of trouble here, but it's the d orbitals that are going to be a bit more complicated. So I'm going to show you that right now, how to do the d's. Okay, so remember, there's always one s orbital, 3 p orbitals, and how many d orbitals? 5. Okay, so I'm going to show you guys how to draw 5 now. First, you have to learn their names. You can't draw it if you don't know their names, because their names are going to really help you tremendously in how to draw them. Okay, so learn their names first. DXZ, UYZ, DXY, DX squared minus Y squared, and DZ squared. 1, 2, 3, 4, 5. So the 5 d orbitals. Okay. And again, what are orbitals, guys? 3D region of space where you can probably find the electron. Okay. Okay, so the D, notice how the names are. It's just X, Y, Z, your Cartesian coordinates, and then it's a scramble of any two, okay, for these. And then the last two are different. It's X squared minus Y squared and Z squared. So you just have to remember that. But these two letters, these two axes tell you where the double peanut or the 4-leaf clover lies, right? It's gonna lie in the XZ plane. So I don't need you to draw it in 3D. 2D is just fine. Draw your x-axis here, your z-axis here, okay? And draw your double peanut, dxz. Okay, let's draw dyz. Okay, so just change your axis. So I'll still keep this one as z, but now this is going to be y because it's the dyz I'm drawing. And again, just draw the double peanut or the 4-leaf clover. And notice how I'm drawing the 4-leaf clovers. I'm drawing them in between the axes. Okay, so that's what you got to remember is that these are off axis. Okay, so dxy is next. So now I'll change this to x. I'll change this to y. And again, it's off axis. So I'm going to do 4-leaf clover off axis. And then I'm going to do now the fourth one, dx squared minus y squared. So again, it's telling you, right? There's an x and the y axis. You see what I mean? Is if you know the name, it's easier to generate the drawing. So dx squared minus y squared is going to look like dxy, except the 4-leaf clover is 45 degrees shifted and it's laying on the axis. Okay, so that's that. You got to remember that these ones are on axis. Axes. Plural, okay? So dx squared minus y squared is this one. And the last one's dz squared. So again, it tells you, it's going to be on the z axis. So draw the dz squared. Remember the dz squared is the odd duckling? where it looks like a P orbital, looks like a PZ, but it has a belt. So just draw a circle around it and label it dz squared. It doesn't even matter if this is x or y, right? It doesn't really matter what you label this. As long as you have this on the z-axis, that's correct. Okay, so those are your 5 d orbitals, right? That you should learn. Go practice that. Definitely going to be tested. All right. And one more time, what are these funny things that we're drawing? We're trying to map out where the electron is in the atom, right? Where we can probably find the electron. 3D region of space, we can probably find the electron. So what does that mean? Can we find the electron here? No, it's in no man's land. We can find an electron here. We find an electron here, here, here. Okay. But we cannot find the electron here or here, right? It has nodal planes. Okay. Same thing here, right? Can't find the electron here, only in these 4 lobes. In the dz squared, right? You can find the electron here, here, and also in the belt region. Okay. Okay, so that's it for this one. I'll see you in the next video.